All right, so we kind of didn't get to these last examples, so I want to do that right now. Just remember, though, this formula is for an infinite geometric series, the sum of an infinite geometric series. If your R value is between -1 and 1, it converges. If it's not between -1 and +1, it diverges. Okay, so don't use this formula if it diverges. All right, examples. So first of all, let's verify that this is in fact geometric. Multiply by 5 over 6, multiply by 5 over 6, multiply by 5 over 6. So my common multiplier, my common ratio is 5 over 6. My first term is 5. And this formula is actually easier because it doesn't have an n in it. So that's really all we need. My sum, my infinite sum is going to be equal to, first, double check to make sure your R value is between -1 and +1. It is. All right. So the formula is a sub 1 over 1 minus R. 5 over 1 minus 5, 6. That is 5 over 6. 6 minus 5. 6 is 1/6. 5 over 1 multiplied by the reciprocal. So this is going to sum to 30. I'm going to show you that our calculator can actually verify that, maybe. Let's move on though here. So here, I do have a geometric ratio again. I'm multiplying by 7 over 5, multiplying by 7 over 5, multiplying by 7 over 5. So if I had a little more time, I would show you that you could take your first term, 1 minus your common ratio. Actually, I'm just going to do this. 1 over -2/5. 1 over 1 times -5 over 2. So you might say, well, that's just -2.5. And of course, you're going to be wrong. I mean, look at it. These are all positive. There's no way the infinite sum could be -2.5. Your R value here is 7 over 5, which is greater than 1. So all of this work I did here was all nonsense. I was trying to just show you that you can put those numbers in, it's just that they don't have any meaning, and you shouldn't use the formula if your R is not between -1 and +1. So this diverges. The sum is divergent. The sum does not exist. There is no sum. I don't know, however you want to say it. Okay. I'm going to just show you here on one way that you can sometimes use your calculator to find an infinite sum is to write this as a summation. So basically, well, this is a geometric series. Remember, the nth term is a sub n equals a1 times your R to the n minus 1 power. So this would be 5 times 5 over 6 to the n minus 1 power. And if we add these up from 1 to infinity, that is this sum. So if we type that into our calculator, the sum from n equals 1 to infinity of 5 times 5, 6 to the n minus 1 power. Now, normally you would say there's no way the calculator is going to be able to do this, but this is a CAS. It can do some pretty amazing things. It gives you 30. That last example, what was the first term? First term was 1, I think. And then the common ratio was 7/6 or 7/5 or something. I don't know what it was. 7/5. We hit enter here. It says that it equals infinity. What that means is it grows without bound. Technically, does a sum equal infinity? Infinity is not a number, so a lot of times mathematicians will not say that the sum is equal to infinity because it's more correct perhaps to say that the sum grows without bound. Yeah, it diverges. That's a better way to say it. All right. Evaluate and simplify reasonably. So now they're giving it to me in summation notation. If I had the calculator, I could just type this in and not have to worry about it. But of course, I will not give you a calculator on this type of problem on the test. So the first thing I would recommend you do is to write out the first few terms so you don't make any mistakes. So when k is 3, that's the first term. 10 times negative 1/2 to the third power plus 10 times negative 1/2 to the fourth power plus 10 times negative 1/2 to the fifth power plus dot dot dot. And here there is no last term. I can't put in the last term. So the first term is 10 over negative 8, I guess, which would be negative 5/4. So that's the first term. And sometimes people might want to write down the second term too so they can see the common ratio, but I think it's easier to see the common ratio here. When I go from here to here, I take the original, and you can see by just increasing this power by 1, I'm basically just multiplying by a negative 1/2. So my R value is negative 1/2. My first term is negative 5/4. So first of all, does the infinite sum exist? Well, is R between 1 and negative 1? Negative 1/2 is between 1 and negative 1, so we're good. So that means this sum, I don't need to write it like that. My infinite sum is equal to A1 over 1 minus R. So negative 5/4 over 1 minus negative 1/2. I guess you do need to be a little careful here that you don't mess up the simple fraction work here, I guess, right? So negative 5/4 over, so 2/2 plus 1/2 is positive 3/2. Negative 5/4 times 2 over 3 gives me negative 5/6. So this actually converges to a negative sum. My first term is negative, my second term is going to be positive, my third term is going to be negative. Apparently they converge to a negative. So this is the sum from k equals 3 to infinity of 10 times negative 1/2 to the k. Okay? If we wanted to verify that, we could type it into our calculator, but I'm going to I'll let you do that if you want to. All right, next example. Evaluate and simplify reasonably or state that it diverges. All right, so again, I guess we should see, I don't know. Whenever I look at this, I can just look at this value here and say, oh, that's your R value. Well, you got to be a little bit careful about that. If you get something that's like this and you got a 2K, your R value isn't actually always going to be just this base number, because every one increase of k is going to increase this by a square. But in this case, yeah, our R value is 7 over 8. That is definitely bigger than 1. This is going to diverge. If you have a hard time seeing that R value, please write out the first few terms. And you should see that as you go from here to here to here, you're increasing by a factor of 8 over 7. So that's your R value. All right? Let's get this last example in, and so that I wouldn't have too much that I missed in the lecture. Solve the following equation. So we got a sum here. We got a variable as the power of as the base of an exponential function, which is my summation, and it's equal to some number. All right, so let's write this out. Anytime you see the summation notation, write out the first few terms. So when k is 0, this is 2 times x to the 0 is 1, plus 2 times x to the 1, plus 2 times x to the second, plus 2 times x to the third, on and on and on forever to infinity. Okay. I don't know if you could divide everything by 2 if you wanted. I don't know if that, we don't need to. Let's just not do that. So you should recognize that this is a geometric sequence. My first term is 2, and my common multiplier is x. So I want to use the formula S equals A sub 1 over 1 minus R, but I can only use it if X is between negative 1 and 1. Well, I don't know what X is. So what I need to do here is I need to assume that it's between negative 1 and 1, use this formula, and then double check to make sure that it is actually between negative 1 and 1 to see if the solution is valid. So this sum is going to be, if it exists, it's going to be 2 over 1 minus x. So let's solve this for x. 2 equals 10 minus 10x, I guess. 10x equals 8. X equals 8 tenths, which is 4 fifths. Okay, so here it is. If this converges, then your x would need to be equal to 4 fifths in order to give you a sum of 10. And if x is equal to 4 fifths, then it does in fact converge. So my x is equal to 4 fifths, and I do have a valid solution to the equation. Okay. This guy here, I would encourage you to read this. I'm not going to read it to you, but he came up with 3,900 of these crazy identities, and this is before. His name is Ramanujan. I always say Ramanujan, but I don't know how to pronounce his name. He was a self-studied. He learned math on his own. Didn't really have advanced math teachers. He was brilliant, obviously, but he would come up with these identities that nobody at the time, well, even nowadays, knows where they came from. And at the time, they couldn't even prove most of them. But it has now since been proved that many of discoveries were proven correct. Some still defy proof by mathematicians today. But just try to fathom these numbers and how this could somehow give you the reciprocal of pi is pretty amazing. Sometimes people use his formulas to estimate pi to a lot of decimal places. Now there's some math theory behind that as well. Like to estimate pi, you have to do infinite series expansions of series, basically. And computers can do it all really quickly. But if you want to get 17 million digits of pi, every term you add has got to add some accuracy to this value. So what you want is you want a series that only takes a small number of terms to get a certain amount of accuracy. Like one expansion might say, okay, you want to estimate 1,000 decimals of pi. One expansion might require 500 terms to get 1,000 decimals of pi. But another one might only require 200 terms of an infinite series to get within 1,000 decimals, 1,000 digits accuracy of pi. So if you can find one that doesn't require as many terms, then a computer can calculate those 200 faster than it can calculate here. So you want to find the right series or sequence to add up to try to get more and more accuracy here efficiently with your computing power. So his formulas are even today were good for that. But there's a movie called The Man Who Knew Infinity. I would recommend it. It's a true story about this remarkable person. He died very young. I always think about what could he have discovered had he lived to be an old man, right? Anyway, that's the video. Good luck with the test.